All right, this video is for AP Calculus, and we're going to talk today about the difference between average and instantaneous rate of change, and also introduce two new theorems. Well, one new theorem, the mean value theorem, and its connection to the intermediate value theorem, which we also covered in a previous video. So first, let's start by defining average rate of change versus instantaneous rate of change. The average rate of change means the average change in the y variable over an interval of the x variable. So if you have an interval, like let's say over here from, here. If you have an interval in x from say 0 to 2, and you want to know what the average rate of change is, then you simply take the point at the left end of the interval, the point at the right end of the interval, and you find the slope, the regular algebra 1 slope, change in y over change in x. The phrase for that is average rate of change. So that specific phrase in calculus means the change in y over the change in x, and it has to be specified over an interval. So the change in y is f at the end, f at 2 minus f at the start, f of 0, divided by the width of the interval, 2 minus 0. Right, now the instantaneous rate of change, that is given at a specific x value. So not at an interval, but at a specific x value. We can define the instantaneous rate of change as the derivative, right? That is the limit as you take these 2 points and move them closer together. So that's called the derivative. We label that f prime of x, and that means that you can use the limit definition, or you can just compute the derivative of the function and then plug in that one value, right? So the difference between average rate of change and instantaneous rate of change is that the instantaneous rate of change occurs at one point, and it's the derivative, and the average rate of change is the average slope over an interval. Okay, so here's an example of a problem to show the difference between the two. Hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t in minutes is given by a differentiable function c in ounces. Selected values of the amount of coffee c are given in this table. So we know at these 5 times how much coffee is in the cup, but we don't know anything about the intermediate times. What is the average rate of change of the amount? So average rate of change, which you shouldn't abbreviate this on the AP test, but I'm going to in this video, average rate of change, AROC, is equal to the amount of coffee at the end of the interval, which is 9, minus the amount of coffee at the beginning of the interval, which is 1, over the width of the interval, which is 9 minus 1. Right, then we can get these values from the table. So this is 6, and then this one is 2, and this is 9 minus 1. Right? And you could just leave the answer like that, but you do have to have the units. This average rate of change is a slope, so its units would be the y unit, in this case it's ounces, per the x unit, which is minutes. Right? And if you do compute that all down, it ends up being 1/2 or 0.5 ounces per minute. So you can leave things unsimplified, but you do need to include units. Okay, then it says estimate the instantaneous rate of change at a single value, t equals 10 minutes. So we really would like to have the derivative, the instantaneous rate of change of c. We would like to find c prime at t. So what we're doing is we're estimating. So you could write this. You could say c prime at t is estimated, so I'm going to use an approximate equals symbol to be, but I'm going to estimate that with an average rate of change. I'm just going to say if t equals 10 is here, then the nearest places I have value for that is 9 and 16, so I can say let's at least find the average rate of change by doing c of 16 minus c of 9 over 16 minus 9. And that means that c of 10 is approximately equal to, let's see, 8 minus 6 over 16 minus 9. And that is also in ounces per minute. Right? And that turns out to be, if you do that in a calculator, 0.286. If you had a calculator and can get that more precisely. Remember, anytime you answer in decimal, if the answer is not exact, you have to round to 3 numbers past the decimal. right? So you can call this the estimate of the instantaneous rate of change, or what C prime of t is approximately. Okay, then in part C it says if the function is found to be actually that the coffee function is 2 times the square root of t, find the instantaneous rate of change at t equals 10 minutes. So now we have an ability to calculate the derivative directly at 10. So I'm going to go ahead and do that. If C of t is, I'm going to change that square root of t to t to the 1/2 so that I can use my derivative rules to compute C prime of t. So that's going to be the constant, and then this derivative is 1/2 t to the negative 1/2, or those cancel to just t to the negative 1/2, which is, because I'm going to plug something in here, the same as 1 over the square root of t. Then that means I can find exactly what this is at 10 minutes. So I'm going to use an equal sign here because I'm finding the exact value, 1 over the square root of 10. And then that is also ounces per minute, because the derivative is a rate of change, right? So it has slope units, y over x. In decimal, this one is 0.316. So that's the true rate of change of coffee versus time, and this is an estimate of that value. And this is just an average over a whole period of time. All right, let's take a look at another topic. Let's compare the intermediate value theorem, which we already know about. We've seen this in a previous video, but we will recover it completely here. And a new theorem called the mean value theorem, which has a special case called Rolle's theorem. So the previous theorem was the intermediate value theorem, which states this: if f is a continuous function over the closed interval a to b, and the endpoints are not the same, f of a and f of b are not the same, then k, and you define k to be any number between those two endpoints, then there must be at least one c in the interval between a and b, such that that c plugged into the function produces that y value of k. It's simply that. It's saying if this has no breaks, and you pick any value between the y's at the ends, there must be an x that produces that y. Now, it doesn't say that there's a unique value. It could be one, it could be multiple values of that, multiple x's that produce that value, and it doesn't give you a way to provide the value. It just is a theorem that guarantees that there is a value that provides that. Okay, and we could use this copy example here to investigate that. AP could ask a question like this: is there a time t equals k in the interval between 0 and 16 when the coffee cup definitely contains 5 ounces of coffee? Right? And if you look at the output values, right, there is, because between 0 and 16, this 5 does appear between 0 and 8, right? The output values are 0 and 8, so there has to be some time in here where this produces that. Now, in order to invoke this theorem, though, we have to show that the conditions for the intermediate value theorem are met. So when you're invoking a theorem, you want to first say something like this: C of t is differentiable. That was stated in the problem. But we're going to say, and therefore is continuous, because for a function to be differentiable, it has to also be continuous over the closed interval from 0 to 16. That is a condition for invoking the intermediate value theorem. The other condition is, so we can say, and the output values are 0 to 8, and this target output value of 5 is between those values. So that's the full condition for invoking the intermediate value theorem. It's a continuous function over the closed interval, and the output value is in between the output values at the ends of the interval. Then we can say, therefore, the intermediate value theorem guarantees a k such that this is between, k is between 0 and 16, the x domain, such that C at that k is equal to the target y of 5 ounces. Okay, so that's how you would want to answer this question if you're asked it on one of our tests or on an AP test. So this is the theorem we were introduced to before. Nothing new there. I want to show that so you can compare it to this new theorem. So this new theorem is called the mean value theorem. Now this is not about showing that the y is, that there's an x that produces the y. Let's just read it and then we'll compare. The mean value theorem says, let f be a continuous on the closed interval from a to b and differentiable on the open interval from a to b. If that's true, then there exists a number c in the x interval such that the derivative at that c is equal to the average rate of change. Right, so that's saying that if you have an interval in x and you compute not the y values at the ends, you compute the average rate of change. In other words, the slope of the secant line. If you take f of b minus f of a over b minus a, what you're doing is finding the slope of this line right here. Then that means that somewhere in here, if you were to look at all the tangent lines, let's say I'm just drawing tangent lines in here, all the tangent lines, all the instantaneous rate of change, there has to be at least one c in that interval where the tangent line slope is equal to the average rate of change slope, which we could call the slope of the secant line. Right, now that's different than the intermediate value theorem. The intermediate value theorem states that there is an x value that just produces a y value. So the intermediate value theorem is about the y value, producing the y value. The mean value theorem is about producing the derivative. So what you're basically saying is the derivative at c is equal to the average rate of change. So the mean value theorem is about the mean rate of change or the average rate of change. Okay, so we'll again look at that. And just like before, we're going to have to show that the conditions are met before we invoke the theorem. So here, same table. Is there a time t equals k in the x interval when the rate of change of the amount of copy equals the average rate of change? Right? And that would be better stated instantaneous rate of change, where the instantaneous rate of change of amount of copy equals the average rate of change justify your answer. So we're going to say, first of all, that we're going to assert the function is continuous and differentiable. And it stated it was differentiable over the entire interval. So we can say c of t is differentiable and therefore also continuous over the closed interval from 0 to 16. That's the first condition. Right? And really, that's the only condition, right? We don't have to say anything about the particular endpoint values. We can just therefore say, therefore, and I'm going to use these dots. 3 dots like that mean therefore. Therefore, the mean value theorem does guarantee a k, where k is between 0 and 16, such that the derivative at k, the derivative of this function, so actually this is the c function, that the derivative of c at time k is equal to the average rate of change, which would be c16 minus c0 over 16 minus 0. Okay. Is there a time? Maybe we should even start by saying yes. So we want to answer their question, and then this is the justification. Yes, because c of k is differentiable and therefore continuous over the interval, the mean value theorem does guarantee a k in the x interval such that the derivative at that k is equal to the average rate of change. And on the second part, if you're further told that the function is c is 2 square root of k, 2, find k. So for part B here, we could say, okay, so since c of t is 2t to the 1/2, that means that c prime of t is going to be equal to 2 times 1/2 t to the negative 1/2, which is, as before, 1 over the square root of t. So then we can say we know that c prime of k is equal to c16 minus c0 over 16 minus 0, because the mean value theorem is guaranteeing that. The derivative is 1 over the square root, and I'll plug a k in there. And to compute this, we're going to take from the table values. At 16, c is 8, and then at 0, it is 0, over 16 minus 0, which is 1/2. So therefore, I'm trying to find a k where the instantaneous rate of change equals the average rate of change. And that means that square root of k would have to be equal to 2, and therefore k would have to be equal to 4. So this is to find the k value. K would be 4. You know what? We should probably attach units to that, because k is a time. So let's call that units. Always best to answer it with units. There's a chance that the rubric will take off if you don't include them. Okay, before we go on to another example of that, a couple of other offshoots. So there is a special case of the mean value theorem. If the average rate of change, so this is the special case where the average rate of change is 0. In other words, slope is 0. If the slope is 0, then that means you can call the mean value theorem Rolle's theorem. Right? So we just said in general, if you had, say, a point here and a point here, right, and you have, and you draw the average rate of change line, mention it to that point, then there's going to be some value where the tangent line is equal to that, right? But if you happen to have that the slope is the same, so let's say that you had, say you had your y's at the two ends of the interval are exactly the same, and that means that the target slope, the average rate of change, is just equal to a slope of 0. So yeah, there might be one or more places where the slope is 0. So this would be the mean value theorem, where you have a non-zero slope for the average rate of change. This case here is Rolle's theorem, although you're welcome to still call it the mean value theorem. You can just use the word mean value theorem, and it applies everywhere. Rolle's is a special case of the mean value, where we have the slope is 0. And even it would apply in this case if the function is just, say, y equals 5, right? That means that the average rate of change is 0, and so you could have any number of points in here that produce that. That's guaranteed by the mean value theorem, and backed by the special case of it, which is called the Rolle's theorem. So Rolle's theorem is just a special case of the mean value theorem. I usually don't really worry about that. I just use the phrase mean value theorem. But you should be aware that Rolle's theorem is a way to label the mean value theorem in the special case where the average rate of change is 0. Okay, let's explore a little bit further the two conditions that the function has to be continuous over the closed or the open interval. But let's look at it again. And okay, so it has to be continuous over the closed interval and differentiable over the open interval. Why the difference between open and closed? This is subtle, but it's worth exploring. We don't usually have that come up as a major point, but I think it's important to talk about once here in the lesson. So here are some examples to show why that might be true. What if we have this? Draw a secant line through the point x is 1 and x is 5 on this piecewise defined function. I'm just going to take this line and make that match. So I'm going to make it match at x is 5 where x is 1 and x is 5. And so here is, if we're defining the interval to be from 1 to 5, this would be the average rate of change, this purple line. Show that there is a point where the derivative equals the slope of the secant line. Is that true? Wait a second. Sorry, I did that wrong. Because notice that at x is 5, at the point where there's a discontinuity, this dot is open, but this dot is filled in. That means that at x is 5, this is providing the y value. So I actually have to make it match that. I have to connect it to actual points. Right, so this is a closed point, and that's a closed point, and it does jump here, but at x is 5, that's the point. So that means that this theorem is going to apply, and there is going to be a value in this interval, right, roughly here at 2.9 or so, maybe 3, where the instantaneous rate of change, the derivative at 3, is equal to the average rate of change of 3 at the purple line. Right? So this function is this function differentiable on the open interval? Yes, because we can define a derivative everywhere from, we can define a derivative here at this value, right? But there's a discontinuity here, which means that since there's an abrupt rate of change, the slope on these two sides are not equal. So this is the actual interval where this is differentiable. Therefore, we can say, yes, this is differentiable from 1 to 5, not including the ends. So it's okay to not include the endpoints in the differentiability, because you just need a point to attach the point. It doesn't matter if the derivative falls apart at the ends. You're only going to use the endpoint itself and not what's happening at the discontinuity here to determine the average rate of change. Okay, so that's why the differentiability condition is open and not closed interval. Here's another example, different function. Okay, let's do the same thing. Let's draw an average rate of change line for that interval from 1 to 5. So that would go from this close point to this close point. So, okay. And there is no place where I can make this meet that average rate of change in that interval, right? I can't attach this anywhere in here, right? So there is no place where that's true. And that's because the problem with differentiability is happening inside the interval, right? So here, we can't say that this is differentiable on this. This is not true. It is continuous over the whole interval, right? So just being continuous alone is not sufficient to show that you have to have an instantaneous rate of change equaling the average rate of change. The reason why there's no value is because it violates this condition for the mean value theorem. Okay, one last example here. Here's a piecewise function. Draw a secant line, this time through the interval from 5 to 7. So let's see, 5 is right here. 7 is right there, so I would go from that point at x is 5 to that point at x is 7. That's the average rate of change. And again, I'm not really going to have any place in this interval from 5 to 7 where I can attach this green line and have it match that slope. So this violates the conditions of the mean value theorem. Right? Okay, is it true that h is differentiable from 5 to 7? Well, on the interval of interest here, it's not differentiable here, but it is differentiable here, which means it's true that this is differentiable from 5 to 7, not including the ends. But is the function continuous on that? And I would say that it does not meet this criteria. It does not meet that one because of the problem within the interval. So this one is true, and this one is not true. These three examples are just meant to show that we need both of these conditions to be true to be able to guarantee that there is a value in the x domain that will produce that derivative that matches the average rate of change. Okay, one final problem. This is also an AP style question. The height of a tree at time t t is given in years, is given by a twice differentiable function h, which just means that the function exists, its derivative exists, and its derivative of derivatives. So h, h prime, and h double prime all exist. You can find those derivatives. Where h of t is measured in meters and t is measured in meters. Selected values are provided in the table. Explain why there must be at least one time in t such that the derivative is equal to 0, and then b says that h of t is equal to 0. Okay, I'm going to copy this twice. We're going to invoke a different theorem for each one. So for part A, let's see, this is about the derivative of h, and so this is going to be the mean value theorem. As soon as I see that that's about the derivative, I think in my mind we should think mean value theorem. Mean value theorem. Okay, so for the mean value theorem, we have to have this condition. We have to be able to state that h of t, so they said h of t is twice differentiable. So h of t is twice differentiable. And I'm going to say, so it is, I don't want to use the word it, twice differentiable, and therefore continuous over the closed interval from 2 to 10, and that's a square brace, and also differentiable over the open interval from 2 to 10. Therefore, well, actually, before we say that, let's compute the average rate of change. So I'm going to use symbols for that. H of, let's see, the top of the interval is 10. H of 10 minus h of 2 over 10 minus 2 is, h of 10 is 15 from the table, h of 2 is 1.5, and then 10 minus 2 is 8. That is, wait a second. Yeah, there's actually a typo in this problem. We're going to change something in this problem because that's not working out. Let's change these times and make this be 3 and 5. Yes, that will work out. So now I'm going to change the wording here. For that typo in the notes, because we have to have, the mean value theorem can only guarantee that the instantaneous rate of change matches the average rate of change over the interval. So I have to have an interval where the average rate of change is equal to 2. And I'm noticing that this is 4, and this is 2, and 4 divided by 4 is 2. This is the interval, actually, where the mean value theorem is going to make it match 2. If I stuck with the original 2 to 10, that is not an average rate of change of 2. So I can't use the mean value theorem to guarantee that. Okay, back to the program here, we can say, since h of t, I'm going to slightly change the wording here, is twice differentiable, it is differentiable, meaning the derivative exists, over the interval in question, which is 3, 5. And it only has to be the open interval. And you can say, and also continuous over the closed interval 3 to 5, because a function can't be differentiable unless it's also continuous. Then we can also say the average rate of change, so that's going to be h of 5 minus h of 3 over 5 minus 3 is equal to 6 minus 2 over 5 minus 3, which is 4 over 2, which is 2. And then we can say, therefore, the mean value theorem guarantees a time such that h prime at that t is equal to the average rate of change of 2. So in order to answer this question, to answer this, we just have to be able to show that the average rate of change matches 2 and that this matches the conditions to invoke the mean value theorem. Okay, and then in part B of the last example here, we are being asked questions about the y value of h being 4. Right, so again, I'm going to change the interval here from, although actually I could leave this one the same, but now I'll leave it the same. So this is from 2 to 10, because this one, the intermediate value theorem will work because 4 is in between. So now we're just saying that if this is a continuous function, if I plug 2 in and I get 1.5, and I plug 15 in for x and I get 15, since 4 is in between there has to be some value in here that produces that 4. This is the intermediate value theorem for this problem. All right, so to invoke that, let's go ahead and write it out properly. So for this one, the conditions are, since h of t is twice differentiable, it is also continuous over the closed interval from 2 to 10. And then you can say, and since 4, the target output, is between the endpoint outputs of 1.5 and 15, the intermediate value theorem guarantees I can't spell that right, guarantees a time between 2 and 10 such that h at that t is equal to the y value of 4. And you know what? Probably should put units on here. Same thing with the last one. And the units here would be meters per year. Okay. All right, that's the last example. There's only so much you can do with these theorems, right? You just have to establish that their conditions are met and you can invoke them. The big thing is that if it's about the derivative, then you're using the mean value theorem. If it's about the y coordinate, the y value, then it's using the intermediate value theorem. Okay, that will wrap up this video.